title of the talk is Einstein, Buddha, and Reality. This talk is largely based on a talk I gave last November at a conference in the Netherlands. I was invited by the Rosicrucians to go there and talk. They found my book, Einstein and Buddha, the Parallel Sayings, and they wanted me to say something about it. So that's where the title comes from. But the subtitle really tells you more about what the talk is really about, and which is to try and find a common non-dual root to both science and religion, which is something that relates to the mission of the center. And the mission of the center has three parts to it. One is to demonstrate that there is a common universal truth that the mystics testify to across all the major religious traditions. And the other is to help foster a community of spiritual practitioners who wish to realize that truth for themselves. And then the third part of the mission is to help foster a new worldview in which science and religion can be seen as different but complementary ways of viewing the same fundamental reality. And that's a non-dual reality. And so the challenge here is to see how both science and religion can be traced back to a non-dual root. So why does the center care about fostering a new worldview? Well, the teachings that the mystics give to individual practitioners are mostly designed to help the individuals come to a realization of the truth for themselves. And that teaching by the mystics is usually given in a response to the students asking the teacher for help because they're suffering, because they're deluded. Now, a worldview can be seen as kind of an analogy to that on a societal scale or a cultural scale. Just as the individual suffers from their individual delusion, our society has maladaptive components that make the society as a whole suffer, and also block or impede individuals from following a spiritual path and realizing the truth for themselves. So if we can find a way to develop a new worldview that you might say is more friendly to the mystical teachings, then this in turn will help individual seekers follow a spiritual path and realize the truth for themselves. And it will hopefully also have beneficial effects for the society as a whole, even people who aren't seekers or mystics. Insofar as the worldview of a society is in harmony with the truth, it will tend to be a more harmonious society and will generally reduce suffering, even for people who aren't mystics. So that's the motivation for developing a new worldview. Now this has some challenges to it. One of the challenges is that there's this division between science and religion. Science plays such a dominant role in our society these days, we can't just dismiss it. And so one of the challenges is to find a new worldview in which science can be seen as compatible with the teachings of the mystics. Now this is complicated a little bit because science just isn't this monolithic thing that came along and is once and for all static. We have different scientific paradigms, both historically and at the present. We have different paradigms that are competing in science. We don't have an ultimate answer from science as to what reality is. And so which paradigm in science are we talking about? Which one is going to be compatible with spirituality or mysticism? So that's one of the challenges. The other is there's a similar challenge with religions. As we all know, there are lots of different religions in humanity, both historically and at present. And the question is, how do we reconcile those with each other? So let's just give a little background. In the West, the division between science and religion, first of all, note that this is a modern division. that has taken place in the Middle Ages. There was a unified worldview in Christendom, and this worldview had the Earth at the center and the cosmos surrounding it, and this was all one integrated package, worldview that dominated the Middle Ages. And then a division occurred, which one way of formulating it might be a division between heaven and earth. So you've got the earth at the center, and this became the province of science, and this is the domain of the material world. And then surrounding the earth, you've got the realm of the heavens, and this is the spiritual world and the domain of religion. And you often hear people, even today, talking about these two different realms that science and religion talk about. They say, well, there's not really a conflict. They talk about two totally different things, and they're totally separate. And that's a way maybe to keep them from fighting with each other, but it's not really a solution to finding one integrated worldview. Another way that this division manifested was Cartesian dualism. Descartes made this fundamental division between material substance and mental substance, or simply mind and matter. And this also came with a bunch of other distinctions, such as between the object and the subject, public knowledge versus private knowledge, facts versus values, and reason versus faith. And these are some of the distinctions that are kind of taken for granted in our common understanding of science and religion and the differences between them. And just to illustrate this, if we were to look at a pot full of some flowers, the primary qualities or objective facts, we might say, are that, well, this pot with flowers has a certain mass, it weighs 5 kilograms, we can measure how big it is, it's maybe 25 centimeters on each side, and so on. And those are considered the objective facts about this, what's really real. And then the secondary qualities are our subjective experience of this, which are things like, well, the flowers are soft, the petals are very soft, and the pot is very hard. We see these different colors, red, white, brown, and so on. So that's how one of the distinctions has kind of rooted itself into modern philosophy, really. So let's start with these different religions and how we'll reconcile those. And I'll just touch on this because that's a topic that the Center really deals with in one of its other points of its mission statement, which is to show that there's this common universal truth at the core of all religions. And so we have these different scriptures from all the different religions, but what all of these point to, the mystics say, is a direct insight that can be gained through by the contemplatives or the mystics of those traditions. And so this is a way to see beyond these differences between the religions. And so we might say that all these different religious traditions of the world have an outer or exoteric aspect to them, which you might say, if you take the teachings in the scriptures literally, for example, that would be an example of an exoteric interpretation of a religion. But the mystics tend to look more towards the esoteric interpretation of these teachings, what they're pointing us to discover in our own experience, for example. And so as you look more to the esoteric aspects of these religions, you find that they have more and more in common. And so that's kind of going more and more towards the center of this mandala here. And at the very center is what you might call the transcendent unity that all of these traditions are pointing to. There's not, as it were, a single common doctrine or teaching that you can speak of that's universal amongst all of them, because the teachings of the mystics are ultimately beyond speech. But they're all pointing to the same transcendent unity, which is why it's called transcendent. And they all have this common way of discovering this. So you might call this a spiritual method. It's an interplay between the teachings of the mystics and our experience. So that we take the teachings and their instructions to go out and do a practice or investigate something. And so then we look in our experience, such as the meditation we did earlier this morning, and we see what we discover. And then that feeds back to either confirm the teachings. It's like, oh wow, now I really understand what that teaching was about. And that's really true, that everything is impermanent, for example. Or it might give us a deeper insight into it. So at the core of these teachings of the mystics, we have some basic fundamental teachings that they testify to. One is that ultimate reality is non-dual. It's beyond what we can conceive of or think about or write down. The other thing they agree on is that what leads to suffering is mistaking imaginary distinctions to be real distinctions. It's not that there aren't distinctions, it's that the nature of these distinctions is misunderstood. We make these distinctions and then we think that they're real. We forget that they're only imaginary, and this leads to our suffering. And also, they teach that we can realize this non-dual truth, each of us. This is possible, and become free of delusion and suffering. So what about the different scientific paradigms? This was the other problem I mentioned earlier. We have Aristotelian physics, which is now considered outmoded and obsolete. And then there's classical Newtonian physics. And more recently, in the 20th century, we had Einstein's theory of relativity and quantum theory. And then, of course, we're going to have some future physics, no doubt. Lots of physicists are working on it, and they're hoping to find string theory or a unified quantum gravity or what have you. And so we have these different theories historically, but also even at present, relativity and quantum theory aren't unified yet, and so we have kind of these conflicting views of what's really going on in the physical world that haven't been reconciled with each other. So what do we do with all this? Well, one thing that behind or underpinning all of these different paradigms of science is really the scientific method that is kind of invariant or unchanging throughout all of these different paradigms. If we come up with a new theory of physics, that won't change the basic scientific method, which is analogous to the method of the mystics in the sense that we have theories or laws in physics, and then we make predictions with them, and then we do an experiment, and we see how they match up with the facts, and then that tells us whether the theory was right or not. It gives us insight into the nature of the theory. It either confirms it, or maybe it helps us refine the theory more, or understand a deeper theory. So this is a way in which there's kind of an analogy between the mystical or esoteric aspect of religion and the scientific approach to understanding reality. But there's a problem here in that some of the scientific core assumptions are different from the core teachings of the mystics. So science, by and large, assumes that the world objectively exists out there. There are planets, there are stars, there are rocks, there are material objects that we study, and the job of science is really to interact with those and find out what their nature is, what the real laws are that govern them, independent of what we might think about them. So the underlying assumption here is that there is this objective world out there, this physical world, and that science's job is to understand that world. And when we understand it, we find laws that govern those, and those too are objective. They're not just made up by us. We want to find the laws that are true, independent of what we might think. And finally, the laws are expressed in mathematical language. And mathematics, as is all language, is based on making distinctions. And distinctions are dualistic. And so all of science, insofar as it's formulated in mathematical language, is dualistic in that sense. So we have a challenge here in reconciling these basic scientific tenets with the mystical teachings. So the first problem is science teaches that there's an objective reality and objective laws that govern it. And this exists independent of the observer, independent of observation. And this is incompatible with teachings of non-duality. If reality is ultimately non-dual, there is no ultimate separation between the observer and the observed. We'll get more into this later. So Einstein, just to back this up a little bit by someone who knows a little bit about science, he said the belief in an external world independent of the perceiving subject is the basis of all natural science. Physics is an attempt conceptually to grasp reality as it is thought, independently of its being observed. In this sense, one speaks of physical reality. So that's his definition of what physics is all about in science. It's really about this observer-independent reality that we're trying to investigate and understand. And as I just said, we have a challenge reconciling that with the teachings of non-duality. And the other problem I just mentioned is that the mathematical language of science is expressed in terms of distinctions in duality, and that's also incompatible with non-duality. Which may not surprise you if you look up the word science in the dictionary and trace its etymology back, you actually find it comes from this Indo-European root word that means to cut or divide. So the very word science has distinction built into its meaning, in addition to it being a word, of course, that distinguishes science from non-science. The very word means to divide, and so scientific knowledge, surprise, surprise, is dualistic. So here's the problem. We have at the core of science this idea of objectivity and duality, and at the core of the mystical teachings we have non-duality, interdependence of things, and so on. And how do we reconcile these? And this really boils down to the question of, can we revision, understand science in a different way that makes it compatible with non-duality, what we might call a non-dual science? Is that possible? Or if we throw out those tenets of science that I was mentioning, does science stop being science anymore in any meaningful sense of the word? So that's the challenge here. Can we specifically understand our theories as something that isn't necessarily talking about an objective reality? Maybe it's talking about something else. Our measurements, can we understand the measurements we perform? If I measure the height of this table to be, say, 1 meter, can we understand that as being not an objective measurement, but as something else? If we admit that our measurements are not objective completely, are we still doing science? Can we still do science without that idea of measurements objectively existing? And mathematics. Can we understand mathematics in a way that connects it all the way back to non-duality in some way? And hopefully by the end of this talk, you'll see that I believe the answers to all these questions is yes. Maybe you'll get a sense of why I think that. So, first let's look at the theory. This idea that science is investigating some kind of objectively existent material reality, some substance that exists out there independent of us. So what does science really say about this? Can we find the substance, say, in a chair? Well, our normal experience of a chair is that, well, it's there, it exists objectively, and if I turn my back and look again, it's still there, and we have a sense that the chair somehow has this existence in and of itself, independent of observation by us. But if we look at this, if, let's say, I take this chair and I disassemble it into its pieces, did I destroy the substance of the chair? No, I just rearranged its parts in a different way. Well, would I call this a chair anymore? No, I would call that the pieces that could be assembled into a chair. I could maybe assemble it into something else if it was a nifty kit. So this isn't a chair, but those are chairs. So where did the chair go? Well, the chair was just an idea, right? When you assemble the pieces into a certain arrangement, you call it a chair. So the chair doesn't have substance. The chair is just a name we give to those pieces in a certain form. So the substance doesn't exist in that arrangement of pieces. The substance, we would say, is still there. Those pieces are what is substantial. Okay, so what if we grind them up? Well, we go through the same analysis as we did. Have we destroyed the substance? Well, no, we'd say the substance is still there. Well, now it's ground up. Okay, so these pieces didn't really have substance. They were just a certain arrangement of these dust particles, right? So they weren't really there. They're a name we give to pieces of cellulose and what have you that are arranged in certain shapes. They're pieces of a chair. And that, just like the chair itself, is an idea. It doesn't have real substance. It's just an idea that we superimpose on reality once it has this certain form. But the dust particles, those are real. They have substance, right? Well, you can see where I'm going with this. You break those up into atoms, right? Okay, well, atoms are real. And these dust particles were just arrangements of certain atoms. And when you arrange the carbon molecules and other molecules in a certain way, you call it cellulose, and you put those together and you call those particles of wood. So the substance isn't really in the wood, it's in the atoms, we would say. And this is the view that the ancient Greeks had, basically. You break everything down into these indestructible, ultimate existence atoms. And they are really eternal substances that exist and rearrange themselves to create everything we see. But basically, that's the bottom. You break everything down to these atoms, and that's where it stops. Well, in the 20th century, the physicists found that that isn't where it stops. You can break up the atom. You can split the atom into subatomic particles. And so the atom isn't substantial. It's just a form of these elementary particles. And you break those up and you study them, and what do you find? Well, there's nothing really left to grasp onto. They transform into each other, they annihilate each other and just turn into energy, and there's nothing really to grasp on here. There isn't a single elementary particle that just exists eternally like the Greeks thought. These transform into each other, and they're really just patterns of what? Well, we don't know. They transform into energy, energy transforms into particles, so neither one is really eternal. It's just this movement, and we don't know what's behind it. It's really a mystery. So we try and grasp onto some substance here, and we never really find it. All we find are these arrangements of things, really, that we then call substantial. It's an imaginary distinction, and we confuse it for reality. So this is a type of delusion if we think that anything here has its own substantial existence. So in this view, the elementary particles are really more like patterns of something we don't know what. And Werner Heisenberg, one of the founders of quantum theory, recognized this. And he said, what's really needed now is to change the fundamental concepts of physics. And he's not talking about the equations here, although those were changing in his day. He was talking about the way we understand reality here, physically. We have to abandon the philosophy of Democritus and the concept of elementary particles. And here he's talking about elementary particles as these eternally existing atoms. Instead, we should accept the idea of fundamental symmetries or patterns, ways that this we don't know what, matter energy, arranges itself and manifests into these patterns. And this is derived from the philosophy of Plato. If you're familiar with his Timaeus dialogue, Plato discusses how atoms originate from geometric forms of really mathematical forms. So this was an idea that Heisenberg traces back to Plato. So what we think of as objectively existing is really just a kind of order, or what the scientists call symmetry. And to get a sense of what's going on here, here's an arrangement of stars, and most of us, when we look at that, we just see, oh, well, there's a collection of, 6 stars. We don't see any more than that. But if we shift the positions here just a little bit, whoa, now something jumps out at us, right? It's more than just a random collection of 6 stars. Now it's the Big Dipper. And so something in our imagination adds something more to what was there than just the stars we saw before. And if you're aware of how that's happening in your mind, you can see really how it happens all the time throughout our day and all experience. When we look at a chair, boom. We superimpose or reify, is the technical philosophical term for this, something existing out there, when really there's just a pattern, and then the mind adds something else on top of it. Connects the dots, so to speak. Here's another example. Here are 3 lines, and they're just 3 lines. But what happens when you move them together, boom, suddenly, they're not just 3 lines. It's the letter A. And we learned this at such an early age to just recognize this pattern. We don't even see the lines anymore. We just see the A. It's so automatic and so ingrained that it's unconscious. And when it's unconscious, then there's this kind of delusion that it has some existence in and of itself, independent of our imaginative activity. So this is a way of understanding what science studies, the object of science, not as something objectively existing, but as a study of order. And really the word cosmos, if you trace its etymology back to the Greek, it simply means order. So the cosmos is just order. And insofar as we superimpose upon that some objectively existing thing, we're adding more to it that is unnecessary. It's sufficient just to recognize the order there. And Niels Bohr even said this. He was also one of the contributors to quantum theory. He says physics is to be regarded not so much as the study of something a priori given, in other words, an external world that's already out there, but rather as the development of methods for ordering and surveying our experience. So it's a method of just understanding the order in experience rather than imagining something already exists out there beforehand. So let's consider now physical properties. So we might say, we might admit, okay, that's somewhat convincing, this chair and so on, it doesn't really exist. But what about things like, if I measure it, it has certain properties, and those always exist, right? Those are objective properties of objects. But if we look at observation in quantum theory, observation in relativity, observation even in classical physics, and in our own experience, we find that that's not true. So let's start with quantum theory. 2 points. One is, if you study quantum theory, and in particular the so-called measurement problem of quantum theory, we don't have time to go into that in depth, but the study of the measurement problem in quantum theory has to do with this division between the observer and observed. And also quantum theory shows us that the properties that we measure in quantum theory depend on what we decide to measure. So they don't already exist out there. They exist only in relationship to what we decide to measure. So let's look at these in just a little bit more detail. Even before quantum theory, the physicist James Maxwell, who basically developed our whole understanding of electricity and magnetism, he said, in all science we begin with making a certain region the field of our investigations. defining clearly our material system. So we start out by basically cutting off a region of the world and saying, this is what I'm going to study. We can't just study the whole world all at once. We have to say, well, this is I'm going to study this chair. I'm going to study this, this piece of material. So for example, we might decide to study an atom, and we're going to study it with this device called a Geiger counter. And so we've divided the world now into the system or the object, which is the atom, and the measuring device or the subject or the observer, the Geiger counter. And so the Geiger counter is sitting there waiting, observing, watching for this atom to decay. It's a radioactive atom, so it'll decay and emit a particle that the Geiger counter will detect and it'll go click. So this is a simple division between the observer and the observed. That division isn't built into nature. Nature doesn't tell us you have to draw the line here. We decided to draw the line here. And the famous Schrodinger's cat paradox illustrates how uncomfortable it can be to admit that this distinction can be drawn in different places. So here's briefly how it goes. We again have the system, which is marked off by the box up there with the atom in it, and the Geiger counter. But then we hook up a hammer to the Geiger counter, and it's going to drop and break a poison bottle. And this poor cat may or may not be alive when that happens. So Schrodinger set up the system, and instead of drawing the line of the system around just the atom, he drew the line so that it included not only the Geiger counter, but also the hammer, and the poison bottle, and the cat. And so now they're all in the system. And according to quantum mechanics, this has no definite state until it's observed. So as long as it's unobserved, this cat exists in what's technically called a quantum superposition of alive and dead states. And the physicist John Bell, who developed this famous theorem called Bell's theorem that kind of helped people understand this phenomenon of quantum non-locality, he said that the subject-object distinction, that distinction we were just illustrating between the system and the measuring device moving around, this is at the very root of the unease that many people feel about quantum theory. Some such distinction is dictated by the theory, but exactly when or where to make it is not prescribed. So that's the important part. The theory doesn't tell us where to draw this distinction, or when to draw this distinction, or really whether the distinction exists in reality at all. It's just that to do science, we need to draw this distinction. We need to draw the distinction. It's not that we go out there and find the distinction that exists in reality. It's that we draw this distinction for the purposes of engaging in this activity we call science. And quantum theory really brings this out in a dramatic way. And it's interesting, if you look at some of the mystics, they say some similar things. Like D.T. Suzuki says, we generally distinguish between inner and outer, but the distinction's no more than a form of thought construction. Change the position, and what is inner is outer, and what is outer is inner. In quantum theory, you change the distinction between the measuring device and the system, and the whole description of what's going on changes. So that's the first point. This distinction between the observer and observed isn't some objectively existing thing out there. It's something we add. And the second point is the observer dependence of our measurements. So Heisenberg, he's the physicist who came up with the uncertainty principle. And he said that we have to remember what we observe is not nature in itself, nature existing objectively already out there, but nature exposed to our method of questioning. So we choose a method to question, and nature responds with a certain result that is dependent upon our method of questioning. So let's investigate that a little bit further, using his principle of indeterminacy, or uncertainty, as some people call it. This equation says that the uncertainty in the position multiplied by the uncertainty in the momentum is always greater than a certain constant, Planck's constant over 2. So what that means is if I make one choice for a measurement, let's say measurement choice A, I want to measure the momentum of a particle very precisely. In other words, how fast it's going. So I do an experiment and I measure how fast it's going, and the delta P here, this represents how precise my measurement is. I decided to measure that precisely, so this is a pretty narrow, it's like plus or minus, say, 2. Now if I determine the momentum very precisely, that uncertainty principle says that, well, now the position is undetermined. So this delta x, in yellow here, I'm not sure how well you can see that, but you can see that this is spread out. So we don't know where it will be anymore. Now conversely, I could have decided, I could have made a totally different choice. I said, well, instead of measuring its momentum, let me measure its position. So I do that, and the opposite thing happens. I get a very narrow position, and then the momentum is smeared out. And what quantum theory says is that that isn't actually a result of merely our disturbance of the system, that those properties didn't even exist independent of our inquiry. That's why John Wheeler said that one can observe one feature of nature, or the complementary feature, position or momentum, but not both simultaneously. What we choose to measure has an irretrievable consequence for what we will find. He also called this our participatory view of physics. So in summary, quantum theory has shown us that this distinction between the observer and observed is not some objectively existing thing, and that how we decide to observe determines the measurement results, at least in some respects. So these observed values don't have a kind of existence independent of observation the way we normally think they do. Now, some people think that this is only some property of this weird quantum mechanical theory, but in fact, if you look at other theories in physics, you can find this also. So relativity, for example, this is Einstein's special theory of relativity. You find that physical properties there also exist independent on what's called the reference frame that we decide to observe them from. And nature doesn't dictate which reference frame is the correct one. There is no correct reference frame. This is something we choose. So to illustrate this, let's consider this example of a boxcar. If we are in a reference frame that is not moving with respect to the boxcar, now when I say not moving with respect to the boxcar, this might mean that we're both blasting through space really fast, orbiting the Earth or something. But we're not moving relative to the boxcar, that's all that matters. And this is represented by the fact that our velocity is 0 times the speed of light. And in that reference frame, we can measure the length of the boxcar, and it's 50 feet, and we can measure its weight, and it's 30 tons. Now, if we change our reference frame, so we're no longer at rest with respect to the boxcar, but now we're moving past the boxcar pretty fast, at like 0.8 the speed of light. The speed of light's really fast, so this is really trucking along, faster than any train can go. Now the boxcar is 30 feet long, and it weighs 50 tons. So when we think of something like a boxcar having a certain length, or having a certain mass, that's only relative to a particular frame of reference. It doesn't objectively have those independent of any frame of reference. Those are properties that only exist independent on a upon a particular point of view, you might say. They don't have an independently existing existence. And Einstein emphasizes that this coordinate system, this reference frame, doesn't conform to anything real. The laws of nature have never had and still do not have a preferential coordinate system. So you can't go out there and find some reference frame and say, well, this is the real one, and all the other ones are kind of pseudo-reference frames. This is the reference frame where everything has its real value, and all the other ones are just relative to that. No, he's saying there is no preferred reference frame. The Earth isn't at rest any more than the sun is at rest. You can choose either reference frame. They're both correct. And so in this sense, the Copernican revolution wasn't a complete revolution yet. Einstein went once beyond that and he said, well, you can't say the sun is at rest any more than the Earth is at rest. You're free to choose either one of those reference systems, but neither one is true in any objective sense. So now let's look at classical physics. We might say, oh, well, those quantum theory and relativity, that's all weird, kind of modern, funky 20th century physics. That doesn't really apply to things like tables. But let's take a look. Let's see what happens here in classical physics. Can we find that the measurements even of simple things using rulers also have this property? Well, let's look. What is a measurement and how do we make them? So instead of using vague qualitative terms like tall and short, a measurement is really a way of making things quantitatively precise. And the way we do that is we select a measurement device, we follow a particular measurement procedure, and then we record the measurement result, a number. So for example, we pick a ruler as our measurement device, and our measurement procedure is to put the ruler up next to the horse. In this case, we're measuring the height of a horse, and then we read off the recorded result. We read off the number 60. Say, okay, we've performed a measurement now. Well, now what can happen, and this is where it gets interesting, what can happen is our friend can measure the height of the horse and say, no, the height is 14 1/4. We're like, whoa, that's nowhere near 60. Something went wrong here. So what went wrong? Did they measure that other horse? They said, no. They measured the same horse. We're like, well, something's fishy going on here, right? So what went wrong? Getting such totally different results. Now notice we don't like this, because in science, we want these results to be objective. And so we want to get to the root of the difference here and figure out how to fix it, right? So what we find out after we talk a little bit with our friend is that we were measuring in inches and they were measuring in hands. I don't know if you know, but they used to measure a horse's height in hands. And so sure enough, if you measure the same horse in hands, you'll get roughly 14 1/4 if you measure in inches to be 60. It's about the same. So if you convert the 14 1/4 hands to inches, you actually get 57, which relieves us a little bit. We're not totally bonkers here. So 60 and 57, okay, well that's a little more comfortable. So this points out the fact that when we make a measurement, we are implicitly choosing our units of measurement. Nature doesn't choose those for us. We have to make a choice. We have to say, okay, we're going to measure, and we're going to choose to measure in hands, or we're going to choose to measure in inches. And in order for us to agree about what our measurement result is, we have to agree on the units. And if we were to choose different units, we'd get different results. So now what about the measurement procedure? Now notice we still had a difference here, 60 inches and 50 inches. And so we're still not totally comfortable. It's in the ballpark, but still, really, 3 inches, that's kind of a lot to be missing. So we ask, well, how did you perform your measurement? And they say, well, I went over to the horse and I measured up to this certain point. And we say, oh, well, I actually measured up to this next point on the back of the horse. And so we had different procedures for measuring. We actually read off at different places on the horse. And so if we specify our measurement procedure, no, nature didn't dictate to us where we measure the height of the horse from. We could have chosen the top of the ear, for example. People don't do that because the horse's head, moves a lot. So it's hard to get a repeatable measurement that way. So people chose this other point on the horse to get a more repeatable measurement. And so if we both agree on this uniform measurement procedure, then we can get closer results, 58 inches and 57 inches. Turned out the 60-inch measurement that I made was using not the standard point on the horse. And so once I corrected that, and we're both on the same page now about where we mark off the ruler on the horse, then now we're a lot closer, and this is a lot more comfortable, within an inch. Not bad, but it's still not the same. So how do we account for this difference? Well, we dig deeper, and we find that, well, my ruler was calibrated against the imperial yard, an inch defined as 1/36th of an imperial yard. And their inch was defined as 0.0254 of the prototype meter in Paris. So these are two different measurement standards, and which explains why we get different results. Actually, these numbers aren't correct, by the way. These are just simple examples. These would be much, much closer. But the point here is that if we are both defining our inches differently in terms of a different measurement standard, then we can get different results. And part of performing science is that everyone, in order for the measurements to make sense, everyone has to agree, like, okay, we're measuring inches, and my ruler is calibrated against the standard ruler that we can all trace back to the same ruler somewhere. So we're all on the same page, so to speak. We're all measuring the same thing in the same way, using the same units, and this is all something we decide to agree on. Nature doesn't tell us we have to do it this way. So this is illustrating the fact that we choose these standards, not nature. And so in classical physics, nature doesn't dictate a particular procedure for measuring or the units. And so these empirical properties, namely the height of the horse, doesn't exist independently. It exists independence, not independent, but independence upon all of those choices we made about the units and the procedure and so on. So they don't have this objective existence we normally think they do. So in all these theories of science, quantum theory, relativity theory, classical physics, we find that these properties don't just exist out there. They exist only in relationship to our methods of observing. And those methods aren't dictated by nature. We choose them. So we're starting to get a sense of how science actually works. We have these preconceptions about these tenets of science, that things actually exist out there, that measurement values actually have some existence in themselves, but as we investigate this closer, we find that that's not actually the case. So in this new view of science, we could say, the theories don't describe an objectively existing world of substances, but these patterns of order. And measurement does not determine some kind of properties of objects that exist independent of observation. Rather, they reveal properties relative to our methods of investigation. And quantum theory especially shows that this subject-object division is something that we decide to impose on the world and doesn't exist out there. Now, there's a tendency when people hear about all of this dependence upon the observer, especially in quantum theory, that they think, well, they can just dream up the world however they like and manifest a Mercedes. But it doesn't quite work that way, because the repeatability and reliability of the measurements is the result of us all agreeing to make the same choice. And if we didn't make the same choice, we wouldn't be doing science anymore. We'd just be having fantasies. So these empirical measurements we make are objective and reliable only relative to our observational frame of reference that we've all agreed on. So if you want to make up your own units, make up your own procedures, and do all sorts of things, you can come up with a whole new world you'll be living with. It's just you won't be able to talk with anyone else. It won't be understood. And they'll think you're crazy. Now that doesn't mean that you are. It just means that you're very idiosyncratic at the very least. So we choose these distinctions. And it's important for doing science that we choose them in a stable, consistent way. Because as Wolfgang Pauli said, the instrument of observation must possess a higher degree of stability than the system observed. So if I'm always redefining my inch, and I go out and I make a measurement today, then I didn't like that definition of the inch, let me change it. And then I go out and make another measurement, then another, I'll get all sorts of crazy numbers as a result. I won't be able to make sense of any of it. I have to have a reliable, stable definition of these units in order to be able to basically know whether the variability in the results is attributed to the subject or to the object. If the measurement devices or procedures are variable, then I won't know if my numbers are varying, whether that's because my device was faulty or because the horse was actually growing. But if I fix my measuring devices and I make them very stable, very reliable, then if I get different measurements from day to day, I know I can attribute that to the horse. Oh, my horse is growing. So it's important to do science that the methods we use are very stable and reliable. And they need to be more stable than what we're observing. So now we come to this last point, which is the nature of mathematics. Both the theory and the measurements use mathematics in at least the physical sciences. And the theory uses equations that are mathematical to describe and characterize the order that we discover. And the measurements use numbers, which are mathematics, to quantitatively characterize the properties of things that we're studying. And this idea of physics as mathematics, or as mathematics as fundamental to science, goes back to Galileo, who said that the universe cannot be understood unless one first learns to comprehend the language in which it is written. It is written in the language of mathematics. And it goes back even further to Pythagoras, who said simply, everything is number. And if you understand how number is involved in the making of distinctions, then you can see how he might have thought this. So, for example, he studied music and musical strings, and if you're familiar with musical theory, you know that if you pluck a string and then pinch it in half and pluck that, you get exactly one octave above and so forth. And these harmonious tones correspond to precise mathematical ratios. And so he was fascinated by this and decided that the whole world and the harmonious relationships between things were exactly this. They were mathematical proportions, symmetries, and so on. And we find this today in the atom. There's this formula that describes the vibration of an atom called the Rydberg formula. It says for the helium atom, you plug in integers into this formula and you get the vibration that's emitted when an electron jumps from one energy level to another. It sends off a vibration, kind of like when you pluck a guitar string. It sends off an auditory vibration. This is a vibration of light. And so the atom is kind of tuned in these mathematical ratios, just like the guitar is. And so this is even true on the atomic scale, that these things are vibrating according to mathematics. So we have the theory and the laws are interacting through predictions and confirmations, and both of these are based on mathematics. We have the mathematical equations, which is the language used to describe our theories, and then we have the mathematical quantities, the numbers, which are used to describe our measurement results. And then these relate to each other. We plug the numbers into the equation, or the equation predicts some numbers, and they interact on a kind of mathematical level here. And so what's going on the top level there with science is kind of underpinned by this mathematical relationship between the equations and the numbers that we measure, between the theory and the experiment. So really, mathematics is the foundation of what science is doing. The objects that we're studying, the objects of science, really can be conceived of as arrangements or sets of atoms in a particular arrangement. And the atoms themselves are these patterns of energy according to these symmetries, as we discussed earlier. And these symmetries are really mathematical expressions, and so it really ends up being mathematics at the bottom here that is ultimately what things are kind of made of, you might say. So if everything is made of number, we can also see that every number is a kind of distinction. There's a way you can, in modern set theory, the formulation of one way to formulate the integers is to describe them as sets, which are really just ways of making distinctions. So 0 is what's called the empty set, the set of nothing. And then 1 is the set of 0, which is the set of nothing. And then 2 is the set of 0 and 1, which is the set of nothing and the set of nothing. And it continues like this. I won't say that one. But you can imagine what 100 looks like. In any case, all the numbers are ultimately described just in terms of these distinctions, these sets. You're just making sets upon sets upon sets upon sets. And what's inside of the first set? Nothing. So there's not really any substance at the ground of it. It's just this making of sets, this imagining of distinctions around things. And so these numbers are just forms of nothing. So what we end up with here is that if the laws are mathematical and the numbers are mathematical, we can even discover that the logic we use to reason can be described in terms of distinctions as well. And there's this book called The Laws of Form, and the mathematician who wrote that basically demonstrated that the laws of Boolean algebra, which is basic logic, can be seen as making of distinctions. For example, we negate truth to get false, and that negation is a distinction. We distinguish true from false. And he actually developed this into a kind of mathematics of distinction, in which you can not only express the laws of logic, but also the objects that these laws are acting upon. So your numbers transform into other numbers through these distinctions. The numbers are distinctions. The transformations of numbers into numbers are distinctions. And so it's just a whole system of distinctions. And so why would we want to bother to do this? Well, the reason is that these distinctions are a way of unifying our understanding of science and distilling it down to one important concept. So we saw that measurement is a standardized way we impose distinctions on the world. We measure things using numbers, and those numbers are distinctions. So this is a way of uniformly drawing distinctions in particular ways that we all agree on. And then we correlate those distinctions, we get numbers, and we correlate those with each other to get laws, and those correlations are distinctions. And so science is really about these distinctions and relating them to each other in consistent ways. So we don't measure distinctions, we use distinctions to measure. We don't experience distinctions, we use distinctions to experience. So we can boil down science to mathematics, and then at the bottom, mathematics can be boiled down to distinction, and then we have a problem. We've boiled this all down to what you might call this fundamental duality, making a distinction. How do we reconcile that with non-duality? So I've led you all up to this point. Hopefully you're still awake. But the beauty of this is that now we just have one problem. Instead of all this confusion of science and religion and paradigms and all of this crazy stuff, now we just have one problem. How do we reconcile making a distinction with non-duality? What is the nature of distinction? That's what this all boils down to. That's the $1,000, million question. So let's look and see whether distinctions really exist. We investigated to see if the chair really existed and had substance and so on. Let's do the same with distinctions. So consider the distinction between the United States and Canada. Does it objectively exist? Well, we all know that the border can be redrawn, that in fact several hundred years ago the border didn't even exist. You didn't even have the countries. You just had North America, this unexplored land. So this is a distinction that's imaginary. It was constructed by us as a society, and we agree upon it. Now, you can't just arbitrarily ignore that as an individual and say, you know, I think I'd like to draw the distinction between the US and Canada somewhere else today, and then just go about expecting that to work very well. So in that sense, it has the quality of being objective, in the sense that it's not completely arbitrary, because it's a distinction that we've collectively agreed upon. And if you just walk across what everyone else thinks is the border and tell the customs that you've defined it differently that day, they're not going to take that as a very good explanation for your actions. So that distinction is not objectively real, and yet it has this quality of reality to it because we agree on how to draw it. And that's very analogous to the scientific distinctions that we make. We all agree on how to make distinctions in order to count. We all agree on how to make distinctions in order to make all of these scientific observations, and that's why we can get the same results. And you can take this further into our own experience and look at more kind of fundamental distinctions in our experience, like land and sea. We have this tendency to think of these as somehow, well, there must be really a distinction there somewhere. But just like looking for the substance of the chair, if you go out and try and find it, you know, well, the ocean's coming in and out, and well, where is that distinction? And you can get fancy and try and define it in terms of liquid and solid, but where really is the phase change between liquid and solid? Well, it depends on temperature and pressure and all of these other conditions, and you won't ever really be able to nail it down, either in time or in place, if you really investigate and try and find this distinction. Now, roughly, we can draw it in a certain way and get away with it for all practical purposes, but that doesn't mean it has an objective existence. That's another matter completely. So we can't say exactly where it is. And the same is true for the distinction between night and day. If we're stuck in one place on the Earth, we can all agree, well, the sun rises, the sun sets, and so on. No problem. But if we're out in space, it's not so clear anymore when the sun rises and sets, if we're orbiting the Earth. And then if we're on the moon, it's a whole different story. So these distinctions are relative to where we are and how we choose to define them. So the upshot is that nature doesn't dictate these distinctions. We imagine them and superimpose them on reality, just like the distinction here between blue and green. Where do you draw that distinction? Or do you draw it at all? Some people would not draw a distinction between these two. They'd say those are shades of the same color. They'd say there's no real distinction to be drawn there. So these don't exist objectively out there. And Shankara, the Hindu mystic, said there's neither seer nor seen nor seeing. There's but one reality, changeless, formless, and absolute. How can it be divided? So what we're saying here is it isn't divided in reality, it's divided in imagination. And that is how we reconcile distinction with non-duality. We recognize it's imaginary. From non-duality, we imagine distinction. From imagined distinctions arises numbers and forms. Using those, we can measure and theorize, and science can thus be rooted in non-duality. So, to get back to the very beginning, what about science and religion? Well, the scientific paradigms are based on this general idea of science as being mathematical, and that's ultimately traced back to distinction, which is rooted in non-duality. And similarly, the religions are expressed in terms of teachings that are words that are made of distinctions, and this is a symbolic language, and those teachings are the basis of the religions. So I won't go into exploring that whole branch of it here, because the mystics have already done a very nice job of tracing their teachings back to non-duality. The challenge was over here with science, tracing it back to non-duality. So rather than making some connection between, say, quantum theory and Eastern religions, parallels, and this sort of thing at the superficial level, what this does is it goes to the very root of them both, and it traces them back and unifies them there. So that is really what I had to say today.